Okay, let's have some fun with group theory. Let's prove some theorems. So what's going on here? We start off. We've got the definition of a group here, and there are these 5 axioms. And of course, if you're not thinking, you might think, oh, I'm going to have to learn all the names of these axioms and keep kind of going back up here and looking to see what the axioms are called. But if you engage your brain about the name of these axioms, you can kind of guess what these axioms like. The point about 1 mul is it's 1 times A is A, and mul 1 is A times 1, because the 1 comes after the mul in mul 1. These are named in sort of sensible ways. Inv mul self is all, I don't know. Once you get used to it, you find you don't have to keep referring back to what these axioms are called. You realise that the names of the axioms as saying the statements of the results they're proving. So let's get going. Inv mul cancel left. How are we going to prove that? We've got to prove that A inverse times A times B is B. Well, I guess A inverse times A is the identity. So we need to start off with associativity. The brackets are in the wrong place, right? We want to cancel the A inverse and the A. And the thing about associativity is it pushes brackets to the right, so we need to rewrite Mullersock that way there. And now, although you can't see it because Lean doesn't print them, now the brackets around the A inverse times A. And so now we could rewrite inv mul self there, and you see, and that becomes the A inverse A now becomes a 1. And now we've got to prove that 1 times B is B, so this is exact. I guess we could call it 1 mul B. That would be a way of doing it. There we go. We've solved the goal. Or, I mean, if you don't want to do exact 1 mul B, another way, you could apply 1 mul, because that would also work. This is a little bit shorter as well. We could probably also rewrite 1 mul. There, because that once the 1 mul is an equality, it says 1 times A is A for all A. So when we rewrite 1 mul, the goal becomes B equals B, and rewrite tries REFL at the end of it. It tries REFL just to see if it works. And now you see, now everything is rewrite, so we could even do it like this. Put everything in one line, because it's always nice to get 1-line proofs of everything. So there's another proof. But I mean, we've taught these things to the simplifier, right? Inv mul self and 1 mul. These are also known to the simplifier, so we could do after the rewrite Mullersock. There's a chance that the simplifier will do it. There, the simplifier does do it. You see, it's doing the rewrites for us, and the simplifier can be fed extra things to rewrite as well. So probably if I do this, there we go. So there's an even shorter 1-line proof of that lemma. And so now that means now the simplifier knows inv mul cancel left. And you might think that if it knows inv mul cancel left, then it might be able to prove inv. Sorry. Oh, what? It might be able to prove mul inv cancel left. But it probably can't, because you see, as mathematicians we're like, well, obviously these are the same statements, because you just let these A be this A inverse, but it doesn't quite work like that, right? If you let this A be a new variable C, if you let this A be C inverse, then this won't become C, right? This will become C inverse inverse, and we haven't yet proved that C inverse inverse is C. So we're going to have to prove this. I don't think we can use inv mul cancel left to prove mul inv cancel left, but however, I do think we'll be able to do this because it's the same. The proof is the same, right? You rewrite associativity backwards, and then it's just then it just follows from the axioms, each of which is known to the simplifier. So here's a useful. So we've tagged that simp as well. This is a good simp lemma because it's an equality, and the left-hand side is more complex than the right-hand side. This would not, on the other hand, be a good simp lemma. It is an equality, so it passes the basic test, but the left-hand side isn't particularly more complex than the right-hand side. And furthermore, this lemma needs hypotheses, right? This is true for all A and B, mull, inv, cancel, left, but this lemma needs hypotheses, and the simplifier doesn't look at your hypotheses unless you explicitly tell it to. So this would be a lousy simp lemma, and indeed it's not tagged simp. So one way to prove this, I guess we could do have H, B times A times C equals B times A times C there, and I guess the proof of that is we could just do, I guess it could be exact, well, it's not quite Mullersock because the brackets are the wrong way around, so maybe rewrite Mullersock, that would do that. You see, we had two goals there, so we should maybe put that in brackets like that. Or alternatively, we could just, I guess we could just do, let me show you this other syntax for have as well. It's mull, a sock, I guess it would be BAC, except that's not quite right. If you look at the error there, Mullersock BAC says that some left-hand side is some right-hand side, and we want to prove the right-hand side is the left-hand side. So we could probably do this there, because that applies ec.sim. I guess I need to, oh, we can't see that. I'm using ec.sim on Mullersock. So here I'm using, this is dot notation. I'll write something about dot notation in the course notes. It's once I understood it, I realised it was quite a powerful tool. So now we've got this hypothesis H. So why am I suggesting that's a good idea to prove first? Because you can see this has got an A times C, and so we can rewrite H2 at H. And now the A times C has turned into a 1. And we can also rewrite the H1 there at H. And now H has become B times 1 is 1 times C. And so now, of course, we need to use the simplifier. I mean, now we need to use mull 1 and 1 mull, but the simplifier knows those. So we could do simp those at H. And now H is exactly the goal. So we're in the situation where the simplifier solves the goal. The simplifier can reduce a hypothesis. To the goal. So that means I could probably do simpa this using H. There we go. There. So that solved that one. And now what? This one again. This has not been tagged simp. It is an if and only if, and if and only if lemmas are perfectly fine, fair for the simplifier. But it's not really clear which side is simpler than the other side. I mean, this has got, the left-hand side has got more stuff in because it's got A and B and multiplication and 1, and the right-hand side has only got A and B and inverse. On the other hand, you might argue that inverse is somehow a more complicated function than multiplication. I think this is one of those lemmas where sometimes you want to rewrite in one direction and sometimes you want to rewrite in the other direction. And for lemmas like that, it might be safer not to make those simp lemmas. And I don't really see any way of I think we're going to have to split this. So we're going to split an if and only if, and now we've got two. Now we've got two goals. So let's put them into two different. There we are, two different boxes. So what's the proof of this one? I guess intro H is the way to start. And now we've got to prove that A inverse equals B, and this is the proof that I'm wondering if you'll spot. The idea is that the previous lemma is very helpful for us here. We're trying to prove that A inverse equals B, and we know that A times B is 1, but we also know that like A inverse times A is 1, because that's one of the axioms, and so we can use this. We're going to be able to apply left inv ec right inv there. If we apply left inv ec right inv, now we have three goals, and we can kind of see, I suppose we could refine it instead, if you like. We could refine this and then two underscores there. So what you see, this is the one there. The Lean's saying, okay, Lean can't work out. You see, the conclusion of left inv ec right inv is B equals C, but there's an extra variable A involved here. So there's So Lena's saying I can't work out the extra variable. So that variable is this question mark m_1 here. This is an unknown variable. We've got to prove that A inverse times something is 1. We've got to prove that something times B is 1. So this is the one that we can do. That's going to be hypothesis H. So if we put hypothesis H there we go. Then what's left is proving that A inverse times A is 1. And the simplifier will be able to do that because that's one of our axioms. So that's one way. I guess another way of doing it, if we put squeeze simp here, it will remind us that the name of that axiom is inv mul self. So we could have just put inv mul self A there, I think. There we go, that works as well. And in fact, that's now shorter, isn't it? So this could be exact this. There. And in fact, we've done intro H and then this. So I do wonder, can we get rid of this intro H and then get rid of this H as well? There you go. Look at that. There's a super nerdy proof. In fact, because that's exactly this, I could even take this. I don't even need to go into tactic mode. I can do the split. This is how you do term. Sorry, I've gone off piste here. Look, this is how you do term mode split. We can use pointy brackets, and that's exactly that term there. So there we go. And then we can put begin end here instead. So this would be a rather obscure way of doing it. So if I put the sorry here, right, and now I've got to prove the implication the other way. So there you go. There's a slightly obfuscated, but I mean the point is it's shorter. I'm just sort of going into right mathlib. Mathlib likes their proofs to be very short. So now we do intro H here. Actually, we don't do intro H here. H says that A inverse equals B, and B is just a random. We don't know anything about B. It's an arbitrary variable. So we can do the refl trick, can't we? Rintro refl. And now we've got to prove that A times A inverse is 1, and the simplifier will do that for us. Simp there. So there we go. So there's a rather obfuscated proof of that, but you can, if you don't like that obfuscated proof, you can take it apart and make a simpler proof. So what's going on here? We're trying to prove that 1 inverse is 1, and so of course the point is that now we know that A inverse is B if and only if A times B is 1. We can rewrite this. We can rewrite it backwards, and now we've got to prove that 1 times 1 is 1, and that's exact mul 1 or something. So I guess the simplifier will maybe we can do this. There we go, that's done that one. And now inv again, we're trying to prove that the inverse of something is something else, so it's kind of perfect. In fact, this might work as well. Let's just try it. Let's see if the simplifier can solve everything. Yes, it can. And similarly here, we've got to prove that the inverse of something is something. So we could try missed. We could try this as well, because somehow the first line of the proof I want to apply. Let's try this. Does this work? There we go. So, I mean, there would be. I mean, I suppose this is supposed to be. Let me do at least one of these by hand. Let's rewrite this. There. And now what have I got to prove? I've got to prove that A times B inverse times A inverse is 1. So this is kind of you see, so I can rewrite molosok backwards, I suppose. And now, where are the brackets now? Yeah, so this is kind of horrible, in fact. Rewrite molosok. Yeah, I don't want to do that. I want to rewrite. If I put A here, there we go, and then we can rewrite B times B. Then we can rewrite, what's that called? Inv mul self or mul inv self. Which one will it be? Yeah, I mean, do we really want to do this? Rewrite mul inv self. Inv self B. I mean, this is somehow the whole point of the simplifier. Now we can rewrite Where's the bracket? The bracket's going to be a times 1, so rewrite mul 1. And then rewrite mul himself again. There, so that does it. So it's actually much simpler, just use the simplifier, isn't it? So let's leave it like that. And now the reason that we've chosen precisely these lemmas for the simplifier is that a theorem of Knuth and Bendix says that if you train a rewrite system on these 10, you see the 5 axioms and then these 5 lemmas, if you train a rewrite system on those 10 facts, then it becomes confluent, and also it also solves the word problem for free groups. So this is a rather elaborate way of saying that what the simplifier will now do. You see, this is what I'm trying to say, is that if you have some random identity which is true in group theory, which doesn't need any hypotheses, but you can just prove it. You can just prove it using the axioms of group. If this is a true theorem in group theory without any hypotheses, then the simplifier can now solve it. That's what I'm trying to say, and that's the theorem of Knuth and Bendix, that these simple lemmas are precisely what we need to solve an arbitrary. You can do your own experiments. You do whatever. Example. You can do your own. You can try some other random identity in group theory, and you'll see that the simplifier can solve it. So here's a fun problem that's often shows up in an example sheet for group theory. Prove that if G is a group with the property that G times G is the identity for all elements of the group, then prove that G is abelian. So why don't we prove that? This G times G is the identity is not actually the useful state. The useful statement is that for all G equals G inverse. That's what we need, and we just proved something like that, right? Where was it? There. A times B is 1 if and only if A inverse equals B. So this is, now we want to write this the other way. I suspect that the rewrite won't work. If I rewrite this as H, I suspect that will fail. Yeah. So there's an interesting thing. Why does that rewrite fail? That rewrite said if A times B is 1, then A inverse equals B. So if we try and rewrite that thing, it should be looking for A times B equals 1, and we can see in H we've got G times G is 1. So why is the rewrite failing? And it's failing because rewrite won't work under a binder, and for all is a binder. Rewrite the for all G is messing things up, but I suspect that the simplifier will do it. Yeah, the simplifier has done it because the simplifier will rewrite under binders. So now we know that for all G inverse is G. So now let's try and prove this. So let's intros A and B, and I've got to prove that A times B is B times A. And basically the thing I want to use is this, right? Mul inv rev says A times B inverse is B inverse times A inverse. So now we could sort of, I mean, SimpH might do it if we're lucky. No, simplify is not quite smart enough. So let's tell it mul inv rev. Does mul inv rev want? Let's try rewrite mul. No. Sorry, I want to rewrite H of A times B. I think that's what I want to do. The other way. There. So I've changed the A times B to A times B inverse. So in fact, and that's right. I want to do this as well, don't I? HA and then HB. There and curses. Rewrite. It's that's interesting. When I rewrite, I think I can do nth rewrite 1 left HA or something. Will that work? Yeah. You see. If I just use the rewrite, what just happened there is I rewrite HA is the same as HA is the same as that A inverse equals A. So HA with the arrow the other way is the same as that A equals A inverse. But if I just, you see that the problem is I have two A's, and if I do the rewrite directly, then it changes both of them. which is kind of annoying. So you can use nth rewrite and then the number to say exactly which one you want to do. Nth rewrite 1 HA and in fact that you see I've got to get rid of that one, of course, and then nth rewrite 1 HB, and now this is and now this is exactly, and now the simplifier will do it right there, because the simplifier knows mul in brev. In fact, the simplest thing to do is once I've done that one, I can just rewrite this one, can't I? There, and now I wonder if simp h will do it now. There you go. So that's a bit shorter. So in fact, I wonder whether simp mul im brev comma h would do that there, and so there we go. I'm sorry, I'm in golfing mode, so now let's try that there. No, that hasn't worked. I see. Yeah, deep recursion has been detected because I've written h backwards and written h forwards. I think I should perhaps stop playing around. We've got something that works here. No, we haven't got something that works here. We've got something that works. Oh dear. Let's keep going back. There we go. That's worked there. I think we should stop there. I think putting yeah. I see that didn't work either. So, well, I said something earlier that worked. It didn't work. So I think we better stop there. But that'll do. So there you go. There's a proof. I should never have started the golfing. So there's a proof of that cute little result in group theory.